So the most convenient circuit configuration to analyze is the Y-Y connected circuit, which we're now going to explore in a lot more detail. And by Y-Y we mean that the load is connected as Y, the source is connected as Y. The remaining three-phase circuit configurations are considerably more challenging to analyze from a KVL, KCL circuit analysis, and typically the technique is to convert them into a Y-Y circuit through a technique known as Y to delta transformations, which we'll also look at. So although Y and delta circuits can be analyzed using KVL, KCL, the Thevenin equivalent all the time, the easiest of them is the Y to Y. And so a common technique is to take whatever your circuit configuration is, whether it be Y delta, delta delta, delta Y, convert that over to a Y-Y network and then do the analysis. So obviously very important in three-phase circuit analysis is this technique of analyzing the most basic, or the Y-Y circuit. So here we have what is called the four-wire Y-Y connected circuit. This is basically the backbone of three-phase power analysis. At first glance, we'll notice that this figure is significantly more complicated than the Y circuit that we've been looking at, so we're going to take some time to really explain all of these terms. The blue box here represents the circuit model that is most commonly used for the three-phase AC source. So this blue box here, everything inside of that is an electrical element meant to represent a three-phase AC source. Right, one phase, two phase, three phase. Each of the phases of the source is composed of an ideal voltage source, VAN, VBN, and VCN. You'll notice there's also a little prime on those. And these three sources are 120 degrees out of phase with their neighbors. So we'll typically A is taken as the reference, VB will be at 120 degrees, and VC will be at negative 120 or positive 240, however you prefer to write that. Additionally, each phase of the source has an internal impedance. Here we've got ZGA, ZGB, ZGC. That's representing the electromechanical characteristics of the source. We'll analyze this circuit model in more detail in later lectures, but what needs to be understood for three-phase circuit analysis is the internal impedance of each of the phase will cause a voltage drop at the output terminals of the phase when there's current flow. So because there's some sort of impedance in series here, the voltage at the output terminals is not going to be the same as the voltage at the output of the source, and that's due to this, at the output of the ideal source, and that's due to this impedance of the generator, ZG. FYI, ZG typically consists of a series inductor and a series resistance, but we'll go into that in a lot of detail in the next module, actually, when we talk about generators. But for right now, all you need to know is that the voltage at this point and the voltage at this point is not the same because of the voltage drop caused by current flow through that impedance element. Right? So. Yeah, so VAN, if I were to measure VAN, it's not the same as VA prime N. So now you kind of see the utility of putting that A prime in there. It is the voltage generated by the phase A of the generator, but it's not the output voltage, right? VAN would be the output voltage. By design of a generator, when companies are building generators, ZGA, ZGB, and ZGC, they're going to be balanced. They're always going to be equal. So that's kind of covers everything in the blue box. Now what we've got are four lines, and these four lines represent the physical wires that connect the three phases and the neutral up. So we've got Z1A, Z1B, and Z1C. Those are the physical wires on the utility poles. And then Z0 represents the impedance of the neutral wire if it is included. Since these wires are composed of metal, they have impedances that are based on both their physical construction, material, and also, interestingly, as we'll find out later, the relative position of the wires to one another and to the ground. We will learn how to develop accurate models for these different transmission line and distribution line configurations in later classes, and like a later module. Typically, what we need to know now is typically the phase impedances are equal, but not the same as the neutral impedance. Z1A will typically equal Z1B, will equal Z1C. There is nothing that can be said about the relationship between the phase impedances and the neutral impedance. So that leaves us the last element, which is just the gray box. We have the load impedances, right? ZA, ZB, and ZC, which are the same as we presented earlier in the lecture. For most circuit analysis, we analyze a balanced load, meaning the load impedances are equal, ZA equals ZB equals ZC. I've said that, a ton of times now. So now what we can do is I've just kind of included this up here for a little bit of reference. We can understand what the circuit schematic represents for the three-phase YY system. We can now write we can use our KVL and KCL equations to calculate all the unknown quantities in this circuit. So that's what we're going to go ahead and do next. So the first thing that we need to do to analyze this circuit is we need to choose a reference point and make it ground. And conventional analysis is that we're going to choose this reference point and make it ground. The neutral of the generator is the technique that is most commonly used. We are going to label that voltage, we're going to label that voltage ground, and the voltage at the connection of the loads is given a name just so we can start referring to it, and it's VN, just standing for the neutral voltage, right? That's the voltage at the some voltage at the neutral. So what we want to do is we want to start by writing step 1 KCL at that node N. And what that means is that we've got this current flowing in, and that's the current in this top line, which was IAA. We've got the current coming in from phase B, which was IBB. We've got the current coming in from phase C, that's ICC. And we're going to say that the neutral current's flowing out, and we call that I0. So that's KCL at node N, right? The sum of the three currents flowing in just have to equal the current flowing out. So these are, again, the line currents, right? So now what we want to do is write equations for each of these line currents. So step 2 is to write equations for the line currents. So step 2. So I'm going to kind of move over here. So IAA, let's start at this one. What is the current flow in IAA? So the voltage here, the total voltage drop across the impedances in that branch, since this is ground, the voltage at this point is VAN. But not that A, it's the prime, right? VAN prime. And then the voltage on the other side is VN. And we divide that by the impedances, which are the generator, the line, and the phase of A. So that's ZGA, right? Impedance of the generator. Impedance of the phase, which is Z1A, or the line, excuse me, the distribution line, and then just the impedance of the phase, which is ZA. Okay. And then we notice that that's going to be the same for all three of these currents. IBB is just VB prime N minus Vn over ZBA plus Z1B plus ZA, and then ICC is going to be VC prime N minus Vn. We're going to divide that by the impedance of the generator for phase C plus the impedance of the transmission or distribution line for phase C plus the load impedance of VC. So we can just rewrite each of these line currents in terms of the voltages at these different nodes. So the next solution, or the next step, is that we just want to substitute these equations into our KCL. Right? So we just want to take our three equations here, plug them into this. So I've run out of room, so I'm just going to clear the slide. And so what you, oh, I left one off. Excuse me. The last is, I forgot to calculate the current in the neutral here. I0 is going to be equal to the voltage at this point minus the voltage at this point, which is ground, divided by the impedance between them, which is just going to be Vn over Z0. Sorry that I forgot that. There are 4 currents, right, not 3. So that's the calculation of that fourth current. So now I can rewrite KCL in terms of these current equations that I've written, which is just going to be Vn over Z0, right? That's I0 is going to be equal to the current in this branch, which we called IAA. In this case, it's going to be VA prime N minus Vn over ZGA plus Z1A plus ZA. And then we've got to take into account the other 2 currents, which are VB prime N minus Vn divided by ZGB plus Z1B plus ZB. So that's the current in this node here. And then we've got the final current, which is due to the C phase, which is VC prime N minus Vn divided by the 3 impedances in that branch, which are ZGC plus Z1C plus ZC, right? So this gives us really what is the general circuit equation for any YY configuration. It's not required that that's actually a balanced load. Most typically we will analyze balanced loads, but because we've included the impedances individually, this is the equation that we would need to solve for any system, whether it's balanced or unbalanced. So this is kind of the mothership here. So write that one down in your notebooks and highlight it and stuff. So what we're going to do though is we're going to assume we're going to make a simplifying assumption right now. Balanced 3-phase assumption. So that says balanced 3-phase. The magnitude of VA prime N is equal to the magnitude of VB prime N, and that's equal to the magnitude of VC prime N. we're going to say the impedances are all the same in the generator, in the wires, and in the load. So that's going to say ZGA is equal to ZGB is equal to ZGC. Next one is Z1A is equal to Z1B is equal to Z1C. And I'll squeeze the last one in right here. It's ZA is equal to ZB is equal to ZC. Sorry that kind of got squeezed in there, but that ZA is equal to ZB is equal to ZC, and I'm just talking about these load impedances, right? These first two assumptions are almost always true. This one's maybe a little bit of a simplification, and in most unbalanced analysis, this is the assumption that we throw out. These two stay the same. This one stays the same. It's this guy that we get rid of. So what we can do is then we can just simplify that and rewrite this equation where all of these voltages are the same, and I'm gonna just come up with some new terminology. I'm gonna say that there is what we call a phase impedance, Z phase, and that's just equal to the sum of those three impedances. So ZGA plus Z1A plus ZA. Right. And that phase impedance is also going to apply to the B phase, and it's also going to apply to the C phase. So I'm just going to, everywhere I see these three terms, I can just replace that with Z phase. So I'm going to rewrite my characteristic equation, Vn over Z0, not Z phase, but Z0, which is the impedance of the neutral line, is equal to V A prime n minus Vn over Z phase plus V A prime B minus Vn over Z phase, and then we've got plus V, I wrote that wrong, it's VB prime n, VC prime n minus Vn over Z phase. Right, and that substitution is just because we're making the simplifying approximation that all three of those are the same. So now I can just cross multiply by Z phase, and I get Vn times Z phase over Z0 is equal to V A prime n minus Vn plus V B prime n minus Vn plus V C prime n minus Vn. So I've got all three of those. I can then combine those. Those are just going to be V A prime n plus V B prime n plus VC prime n. And then there's three of the Vn's, and so I just do minus 3 Vn, and this just would copy straight into that. So I get Va prime n plus Vb prime n plus Vc prime n minus 3 Vn is equal to Vn Z phase over Z0. Okay. So clearing the slide off, what I'm going to do now is I'm just going to move that 3Vn to the other side. So I get Va prime n plus Vb prime n plus Vc prime n before I had a minus 3Vn, but now I'm going to move it to the other side, 3Vn. And then I'm going to add to that the Vn Z0 over Z, Vn Z phase over Z0. So now I have these three phase voltages, right? And remember, these are phasor quantities. VAN is at 0 degrees, VBN is at 120 degrees, VCN is at 240 degrees. So what you'll find is, since they're equal in magnitude and equal to phase, these sum to 0. Those three voltages have to sum to 0, right? We showed that earlier with the sinusoidal relationship between three currents. It holds for the same three voltages because they're 120 degrees out of phase, right? So those all sum to 0 by definition of the three-phase system. So what we end up resulting in is 0 is equal to 3Vn plus Vn times Z phase over Z0. I can factor out the Vn out of that equation, and I get Vn times 3 plus Z phase over Z0. So I end up with the defining equation 0 is equal to Vn times 3 plus Z0, Z phase over Z0. So let's look at this. Not from a math perspective, but from an engineering perspective. We have to put a little bit of practicality into our math equation now, just like we did here. There are no restrictions on Vn. Practically, this could be a positive number, this could be a negative number, and we know that voltages can be both above and below the reference, so they can have either a positive or a negative voltage. Z phase divided by Z0. Remember that Z phase is just those three impedances added together, and Z0 is the impedance of the neutral line. Those are complex numbers, but they're positive complex numbers. That means this term can never be 0. Non-zero term right here. It can't ever be negative either. We're never going to divide a impedance by another impedance and get a negative impedance. So what that tells us is this term, this whole term inside here, is never going to go to 0 itself for the whole term. That means that in this system, if we make the assumption that the system is balanced, meaning the impedances in each branch are the same and the voltages are of the same magnitude but 120 degrees out of phase, which was that assumption, that means Vn has to equal 0 volts. So in this case, the neutral voltage is equal to 0 volts in that analysis, because this term can't go to 0. So in a balanced three-phase circuit, we get Vn is equal to 0 volts. So let's go back to our current equations and write them, because now we know that Vn is equal to 0. Well, previously we had, the three current equations that we had were, I'll just write one. That's I A is equal to V A prime N minus Vn over ZGA plus Z1A plus ZA. So now we know Vn has to be 0. We said that these are all equal in each of the phases, and we replaced that with a term called V phase. So that gives us I AA is just equal to VA and A prime N minus 0, which is VA prime N. And then those are Z phase. And similarly, IBB is just equal to VB prime N over Z phase, and ICC is equal to VC prime N over Z phase. Sorry, I wrote 0 there, but that's a phase. Therefore, the line currents are going to form a balanced set of 3 equations in this analysis. The only difference in the line currents here are that they're going to be out of phase by the same amount that the voltages are, or in this case 120 degrees. So if we know or calculate IAA, we can easily calculate IBB, we can easily calculate ICC, just because we know that the only difference between them is going to be this phase relationship. Remember, VAN is the voltage at 0, VBN is the voltage magnitude at angle 120, and VCN is the voltage magnitude at angle 240. So the only difference between IAA, IBB, and ICC is therefore 120 and 240 degrees. So what that above analysis shows us is that in the case of a balanced 3-phase system, we can determine all the known quantities through the use of what we call a single-phase equivalent circuit. By calculating the known quantities in this equivalent circuit and then applying the known relationships for current and voltages in 3-phase circuits, we can solve for all the unknowns in the entire 3-phase diagram. So we don't actually have to solve that entire circuit, we can just solve this one, which is kind of a relief. One word of caution is advised though. The current in this line here is going to be IAA, right? There's only one loop, not the neutral current. So this does not tell us what the neutral current will be. Some students do think that this line represents the neutral connector. It doesn't. It represents a single phase of the 3-phase system where the current in this line in the top and the current in this line are the bottom. So don't fall into that trap. Okay, so let's do a example of using the single-phase equivalency diagram to do a balanced 3-phase YY analysis. We don't actually have to analyze that whole circuit. We can just use a single-phase equivalent circuit to kind of come up with a solution for one phase, and then we can apply the known relationships between the three phases of the circuit to determine the B and the C phase calculations. So the question is that we have a balanced 3-phase Y-connected source. It has an internal impedance that's associated with the generator windings of 0.2 plus J 0.5 ohms per phase. We'll learn more about where that number comes from later. Just it's an impedance. It's a consequence of the generator being made of actual materials. And internally, this generator has an internal voltage of 120 volts per phase. The generator feeds a balanced 3-phase Y-connected load having an impedance of 39 plus J 28 ohms per phase, so that just represents whatever our load device is that's connected to the circuit. And then of course we have to connect the generator to the load using some sort of cable. In this case, the impedance of the transmission or distribution line is in total lumped 0.8 plus J 1.5 ohms per phase. So we've got all these resistances and inductances. What we want to do now is construct a single-phase equivalency circuit for the system. We then want to calculate all the line currents in the system, calculate the phase voltages at the load. We want to calculate the line voltages at the terminal of the loads. We want to calculate the phase voltages at the terminals of the generator, and calculate the line voltages at the terminals of the generator. So we'll do each of those steps. So A is to calculate the single-phase equivalency diagram. So we know that the generator generated a 120 volts. We're going to draw the A phase, which is the reference phase at 0 degrees. We call this point A prime. Excuse me. We then have the internal impedance of the generator, which we know is represented by 0.2 ohms, and then an inductance of 0.5 ohms. And that's the end. That there represents the end of the generator. This point is A, noting that it's referring to this A being A prime, this being A. That's just a notation that helps us keep track of what the different impedances represent. Now we've got 0.8 ohms, and we've got 1.5 ohms of inductance. And this represents the transmission line. And then we've got the load that we're connected to, which was 39 and 28 ohms of inductance. That's the neutral point. In the single-phase equivalency model, we connect those with a single line. So this represents the A phase. The B phase, the internal impedance is the same, the transmission line impedance is the same, the load impedance is the same. What would be different for the B phase is that the voltage would be 120 at 120 degrees, and for the C phase it would be 120 at angle -120, or 120 at angle 240 degrees. Either of those would work for the other phases, but we don't need to even calculate those. We can just do it with one phase and then apply those results to the other two phases. So let's analyze this circuit. The first thing that we were asked to do was calculate the line current. So I'm going to call the line, you can call the line current whatever you want. Oh, that's A right there. You can call the line current whatever you want. I'm giving it the name IAA. That just is the current flowing in the transmission line. It's from there to there. That's just going to be equal to the voltage at the generator divided by the impedance in the line, 0.2 plus J 0.5 plus 0.8 plus J 1.5 plus 39 plus J 28. And that gives you 120 angle 0 divided by 40 plus J 30 is 2.4 amps at an angle of negative 36.87 degrees. Just a sanity check there. We should have a negative angle on the current because the circuit's inductive. If I want to calculate IBB, which would be the line current flowing in the B phase, it is simply that 2.4 angle negative 36.87, and then you add 120 degrees to the angle, which is the same as multiplying at 1 at an angle 120, and that gives you 2.4 at an angle of 83.13 degrees amps. And then ICC is the current flowing in the C phase, so that's 2.4 angle negative 36.87 times 1 at angle 240, and that gives us 2.4 amps at an angle of 203.13 degrees, which is behind that guy by 120 as well. So that's the line current, right? So this is a Y analysis. We've got I'll try to squeeze it in here. Can't quite fit it in there, so I'm going to draw it a little funny. So we've got a Y source. You know, this here, that's one phase, that's a phase, that's a phase source generator. This represents the transmission line impedance. And then we've got a load connected in a Y shape that each of these is 39.28 ohms, right? And what we've just calculated is the current flow in the line for this circuit. So that's all the line currents. The next step was to calculate the voltages at the terminals of the load, and it wanted to know we wanted to know the line voltage. So if we've got our single phase equivalent diagram, we know that let me just redraw the circuit real fast. We know the voltage across here is just equal to the current through that times the impedance. So we can just say, remember this was A and this was N. VAN is just equal to IAA times the impedance of the A phase, and so that was equal to 2.4 angle negative 36.87 times 39 plus J28, and we get a voltage of 115.22 volts at an angle of negative 1.19 degrees. So that's the voltage in the A phase. The voltage at the of the B phase is V B to N is just going to be that plus 120. An angle, so VB to N is just 115.22 at an angle of 118.81. VCN is going to be the same. We could have also calculated it as just ICC times ZC, which is just going to be 2.4 angle 203.13. The load's balanced, so it's still at 39 plus J28, and that gives us 115.22. Angle 238.81 degrees volts. So that's given us the phase voltages at the loads. That's, if we were to again draw that three-phase equivalency diagram, maybe you can do a better job right here. So the circles represent these AC sinusoidal sources of 120 volts. These little boxes represent the generator impedance. We've got the transmission line impedance. Now we've got our load over here. So what the problem we just solved was what's the voltages measured across the phase? That's like from here to here, right? That would be plus plus minus VCN. The part D asked us to calculate the line voltages at the terminals of the load. So the line voltages, this is the line voltage, plus minus VAB, for example. So what's the line voltage? So the line voltage, we use our relationship between, for a Y circuit, between line and phase voltage, which was just V line is equal to radical 3 at an angle of 30 degrees times V phase. We've got our phase voltages calculated. We did that here. So for example, an example calculation of a line-to-line voltage is just going to be radical 3 angle 30 times the phase voltage, which was VAN, which was 115 .22 at an angle negative 1.19. And that gives us 199. I'm going to write it real small right here. 199.58 volts at an angle of 28.81 degrees. So that's VAB. VBC is just going to be that plus 120 degrees. So if I add 120 degrees to that, I get 148.81. So VBC is just 199.58 at an angle of 148.81. And then VAC from there to there is just going to be that plus another 120 degrees, so 199.58 at an angle of 148.81. Okay, so that takes care of the line currents, the phase voltage at the load, and the line voltages at the load. The next part of the example problem is to calculate the phase voltage at the terminals of the generator. So again, the generator has some internal impedance. So we want to know what's the voltage measured here. What is that voltage? What's the actual output voltage of the generator? We know these guys are all producing 120 volt magnitude voltages, but due to the current flow, there's going to be a little bit of a voltage drop across the internal impedance of the generator. So what's the actual output impedance of that generator, or output voltage of that generator rather? So to calculate that, it's not too difficult. VAN, which is the output terminal voltage of the generator, is just equal to VA prime N, which is the source voltage of the generator, minus the voltage drop across the internal impedance of the generator, which is just that current flow, times the generator's impedance. You know, I wrote ZGA here for the generator's impedance, internal impedance of the generator in phase A. You know, usually that's balanced, so ZGA, ZGB, and ZGC are all the same. In phase A, that was 120 degrees at angle 0 degrees, 120 volts at angle 0 degrees. We calculated the line current in A, which was the same as the phase current because it's a Y-connected system. So that's 2.4 angle negative 36.87 degrees amps. And then we need to multiply that by the generator's impedance, which was given in the problem statement as 0.2 plus J 0.5. And that gives us 118 at an angle of negative 0.32 degrees volts.
So there was a little bit of a phase shift, you know, VAN being 120, and then the output is actually 118 at an angle of -0.32. VBN is just going to be that shifted by 120 degrees. And that's going to be 118 at an angle of 119.68. And VCN, we could do the same calculation as we did there, just add 120. That's probably the easiest way to do it. You know, the other thing you could have done is VC prime N minus ICC times ZGC. So this is going to be 120 at angle 240 minus ICC, which we previously calculated as 2.4 at an angle of 203.13 amps. Multiply that by ZGC. This is a balanced system, so it's 0.2 plus J.5. And what you'll find for that is, not too surprisingly, 118 at an angle of 239.68. So again, that magnitude is always the same in those. So that is the magnitude of the phase voltage at the terminals of the generator. And then the last thing we were asked to do was calculate the line voltages at the terminals of the generator. So again, that's just VAB, lowercase this time because we're over at the generator. VAB is just equal to radical 3 angle 30 degrees times VAN. And that's VAN being, you know, that voltage right there. And so if I multiply radical 3 angle 30 times 118 angle -0.32, I get 205.94 at an angle of 29.68 degrees. So that's the line-to-line voltage as measured at the generator, the magnitude being about 206 volts. VBC is just that shifted by 120 degrees, 205.94, angle 149.68. And then VAC is just this shifted by 120 degrees, would be 205.94, angle 269.68. So that's that use of the single-phase equivalent circuit in a YY connected system.